Hello students, in today's session we'll learn about how to interface keyboards and displays with the microcontroller. First of all, we'll go through interfacing of displays with the 8051 microcontroller. To begin with, let us discuss how to interface LEDs. LED, you know, light emitting diodes, which emits light when the current passes through it. On the screen, it shows that port 0, all the 8 lines, P0.0 to 0.7, that are connected to the 8 LEDs, bank of LEDs. And here you see that the anode is common of all the LEDs. There are mainly two types of displays, common anode and common cathode. In the common anode, logic low is required to turn on the digit. However, in the common cathode, logic high is required to turn on the LED. Now, mainly while using the small microcontroller based systems, we use 7-segment displays. In the display, mainly there are two types, CRT display and 7-segment displays. The CRT displays are preferred when the large data is to be displayed, say in the computers. But for small amount of data, the 7-segment displays are more suitable. There are LCD and LED displays. LCD is called the liquid crystal display. In the LCD, they are mainly used whenever the battery backup is there. However, LEDs are used whenever the light is dim because they emit light. Though the LCDs are having low power consumption, but due to this feature, the 7-segment LED displays are more preferred because they are visible in the dim light also. Now on the screen, in the left hand side, a component is shown, that is the 7-segment LED display for single digit, having total 10 pins. And here in this diagram, the segments are shown, connections for that, starting from A, B, C, D, E, F, G, and H. Normally, the H is used for dot. And the information that is displayed on this 7-segment display, here you can see how the decimal digits that can be displayed 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But in the alphabets, you can see limited characters you can display, A, B, C, D, E, F, H, I, J. In this format, L, then N will be displayed like this, O will be like this, P, R, S, U, Y, and Z. There is a limitation for displaying the alphabets, but that is sufficient for the small systems whenever the less amount of data is to be displayed. Next, let us see how it is interfaced with the microcontroller. In the figure, the microcontroller port 2, that is connected to the 7-segment LED display. Here you can see the 7-segment display, and these are the connections for all the 7 segments. The connection to the dot, that is grounded, and that is how by sending low or high signal you can turn on or off that particular segment. This is the common anode LED display. So logic low is required to turn on that particular segment, and in this way we can display either numbers in between 0 to 9 or required alphabet characters as per requirement. The rest of the signals that are shown here, port 0, port 1, then a reset circuitry, and the on-chip clock oscillator circuitry. Here the 3 signals PSEN, AD, and EA are used. Then this is sufficient for single digit, but commonly we need multiple digit display. Where these LED displays are used, you find in the calculators, on petrol pump, advertisements, and many more. So we need a multiple digit displays for such applications. For that purpose, let us see how the multiple digit displays that can be interfaced with the microcontroller. So that is shown here in this figure. Here you can see the 4-digit display that is interfaced with the microcontroller. Now this is the driver used. Here you can see the port 0 lines that are used to send the signal for individual segments, and you can see all the segments of each digit display that are connected together through a common bus, and the port is used as output port, which will output the 7-segment code that is to be displayed. However, here port 1 is used as the output port for the digit driver. That means at a time single digit will be turned on. Here you can see the transistor, PNP transistor, that is used as a switch for each individual digit, and at a time only single digit that will be driven. So the microcontroller will output the 7-segment code on port 0 that will go to all the 4 digits, but it will not be displayed on all the digits, but this port 1 will decide. So that will output 0 for first, so that will turn on this digit only. Then next, after say 10 to 20 millisecond delay, then next. So at a time only one digit will be on, and this will happen in a round robin fashion. Due to the persistence of vision, we'll find that all the 4 digits are displaying simultaneously. That is how it is used for display purpose. Mainly this is called as the dynamic display. So the current requirement is low as compared to the current requirement in the static display. In the static display, for each individual digit, all the segments need to be turned on for all the time. But here, one by one, only one digit will be turned on at a time. So that saves the current requirement. That's why the multiplexed digit display, that is more preferable than the static displays whenever we use the 7-segment LED displays. So that is how you can interface the 7-segment LED display with the microcontroller. Now, after finishing this, let us discuss about how to interface the keyboards. For interfacing the matrix keyboard, because when we design a small microcontroller based system, we need the matrix keyboard, the hex keypad, for giving input to the microcontroller. How to interface that matrix keyboard, that we will discuss. The keyboards are organized in a matrix of rows and columns. The CPU will process both rows and columns through the ports. We'll see later how the ports are used. When the key is pressed, a row and column will make a contact. If no key is pressed, there is no connection. In the microcontroller, the program stored in the EPROM that will scan the keys continuously on the polling basis, whether any key is pressed or not. To understand that, next we'll see how the 4x4 matrix keyboard that is connected to the two ports. Rows are connected to the output ports and columns of the matrix keyboard are connected to the input ports. Here you can see this is the output port, the rows are connected, and this is the input port where the columns are connected. So this is the 4x4 matrix keyboard. Now here, let us see how the key scanning and identification that is done by the microcontroller through the program. For that, let us go through the next slide. So the microcontroller will continuously check whether any key is pressed or not. To detect the pressed key, initially the microcontroller will send 0 on its output port, and then it reads the column one by one. If the data read from the column is, let us say, bit 0 to 3 all ones, that means there is a no key press, and the process will continue. That means it will remain in the loop to detect the key press. Whenever the one of the column bit is 0, that indicates that the key press has occurred. Now, let us suppose 1101, that is the data available on these D0 to D3 lines. That means the key in the column D1 has been pressed. But then to identify the exact key, the microcontroller will go through the further process. The controller will start from the top row. The low will be outputted on the first row. Then it will read all the columns again. If finds once no key in that row is activated, and the process is moved to the next row. Like that, it will scan all the rows. Then it will send the 0 on the second row, read the columns, checks for the 0. The process will continue. After identification of the row in which the key has been pressed, it will find in which column the key press belongs to. So once you know the row and column, then it can be easily identified, the scan code of that key. That will be then read by the microcontroller, and that is how the key pressed is detected by the microcontroller. To understand more clearly, let us go through the flowchart for this keyboard scanning process. On the screen, what is the keyboard routine where the key press has to be detected. So first, output 0 on all rows. Then it will read the columns, check whether all keys are open or not. If no, that is by mistakes if some key is pressed. For that purpose, to ensure that all keys are open, this loop is used. Whenever it finds all keys are open, yes, then read the columns, check for the key press. If no, go back. Whenever a low is detected on any column, that means the key is pressed, then wait for 20 millisecond delay. What for this delay is required? For key debounce period. Because whenever you press the key, it will take some time to reach to the stable state. So for correct identification, this debounce period is provided. Then it will output the 0 on one of the row, read the column from that row, whether the key is found. If no key is found, go back. Then output 0 on the next row. So like that the process will repeat till the key is found. Once the key is found, that means now you know the row and column of that key, and then you need to convert that ASCII code into the hex, and this is the return. We'll return to the main program. So that is how the keyboard routine that can be written for scanning and identification of the key press in the matrix keyboard. So that's all about the interfacing of the displays and the keyboards with the microcontroller. Thank you.